Swayam Prabha. Digital India. Educated India.
Welcome to lecture 5 of week 8. So, this is the final lecture for this week, and all the momentum that we have been building to finally demonstrate the MATLAB results, the MATLAB plots, some simulation in MATLAB for the CTRs. That's what we are going to do in this lecture. So, before we do that, let us just very briefly review what we had done in the last thing. So, these were the slides for the last class. You see these equations ddx of bx is equal to ax, where x is your vector, which was written in this manner, and we found out that if once we do b inverse a, and what we are calling this as matrix C. Now, we had purposely recast them these equations in a manner which is basically writing the momentum equation first, then the continuity equation in the duct 1 on the airway, then your momentum equation 2 and the continuity equation 2. So, with this arrangement M1, C1, M2, C2, what we get is basically leads to the form where we have your B matrix in this form. So, this gives you, if you set M naught as 0, then we get back the identity matrix, and we need not invert it. You can just simply I times this is just your variable state vector. Now, if M naught is non-zero, then it is good idea to invert the matrix and multiply it with A. So, pre-multiply it with A, so to get C. Now, what we can do is that basically we just need to invoke the function expm minus expm times Ct. So, I have just shown the derivation only, just discussed this derivation in a little bit detail in the last class. So, basically what happens is that your x vector becomes expm times Cx, and what you get is a phi vector, where phi is a constant. Phi is your set of constant phi 1, phi 2, phi 4, which are to be determined from the boundary conditions, basically relating things upstream and downstream. So, now what are those? Basically P 1 rho naught C naught u, P 2 tilde and rho naught C naught u 2 is equal to, let me call this matrix, well, for now I am just writing this guy as like this, and at x is equal to 0, I just have to put 0 to get the phi thing. So, e to the power expm to the power 0, that will just give me I matrix. Remember the definitions that we had the definitions exponential to the power a is your I plus a square by 2 factorial plus a cube by 3 factorial and so on. So, we are just getting what? 0 matrix, So, we can replace expm by I. So, I times identity times, which is a 4 cross 4 and this 4 cross 1 here, we just get back your phi vector. So, phi constant. So, phi constant is nothing but your state vector or the variable vector at x is equal to 0. So, remember your perforated section, something like this, So, this was the section z is equal to 0 and this was z is equal to L. So, this constant can then be your state vectors at x is equal to 0. Okay. We will put all this guy here, isn't it, and then we will put x is equal to expm C matrix times L, and your P 1 rho naught u 1, P 2 rho naught u 2, and x is equal to 0. So, x is equal to L. Now, if you go back to our figure, this was x is equal to L. So, at this point this was x is equal to L exp m L times P1 rho naught C naught U1 tilde and P2. So, this was at x is equal to 0. So, this is x is equal to L. Now, in transfer matrices we usually relate things that are upstream to that at the downstream. So, what we can do from this guy, from this equation, is that if we were to multiply both sides by e to the power minus C L, that is exp m, that is what we can do is that exp m minus, we just put a minus sign and multiply this thing, L being the length, L is the this length, isn't it. So, once we do that, and P1 rho naught C naught U1, P2 rho naught C naught U2 at x is equal to L. Now, this will be equal to what? Exp m, exp minus C L multiplied by exp m in whole of C into L, that becomes exp m to the power 0, that is your identity matrix. So, this will then become your identity times, that is simply your P thing, P1 C1, I mean P1 at x is equal to 0. Okay. So, then here basically that is what we have. So, now writing this in a more arranged manner, this we can write this as exp m. So, all we need to do to solve this thing, of course, perforates. Now, one thing I want to note here is that just provide some general information that perforates has been around since a lot of time. Okay. Perforates have been around since almost like last 30-40 years. It becomes an integral component of all mufflers, but cheap computational power is there only since the past 15-20 years or so. Now, in a lot of packages you have inbuilt commands. For example, in MATLAB, which I have associated with the course, we just use this command exp m and minus C, which is a C matrix, which is really your B inverse A, and this entire matrix, what we can do is that we can call this matrix as, let us say, T1. So, and another thing that just calculate this guy and invert this. So, rather than inversion, you would rather rely on, suppose if we calculated this matrix exp mcl and try to invert that matrix using the command inv, something like this. So, this is the matrix. So, you could have done that, but a more clever technique is just use exp m minus cl, and let us denote this as T1. So, upstream variables, this is your upstream variable and this is your downstream variables. So, so we have related upstream and downstream variables. Now, how do we go about using this information? That is what we have to see. Now, having denoted this matrix as T1, we probably would want to reshuffle a few things, because we just trying to follow the convention available in the literature regarding plane wave analysis of concentric or well perforated mufflers. So, as a result, what we would like to do is basically, if we just reshuffle the matrix in the sense that let me just sort of rub this guy and write it something like this: T11, T12, T13, T14. So, this will become like this. Okay. Now, if we were to just reshuffle this by putting P2 in the second row and getting this guy here, similarly P2 at the downstream will be here, this will be here. So, this will be followed by some sort of a rearrangement of the equations, that is your rows as well as some of the columns. So, if we were to do it, let us see how the final thing or the form that will be amenable to application of boundary conditions would look like. So, here this is looking like this. So, this would be T11 and this would clearly be T31. So, this is a fairly easy thing. So, here since we are moving P2 in the second spot and rho naught C naught U1 tilde in the third spot in the column, we would basically reshuffle. This guy comes here, this guy comes here. So, as a result, what we would really have is T1 13, T1 12, and nothing will happen to this thing. Similarly, this will become T23 and T22, T24 and I am so sorry, my mistake. This will become T33 and 332, 34, because remember we have just interchanged this thing here, this thing comes here, this row, entire row, and we are just shuffling across the different columns. So, this is really your T33, T33 will come in this place and so on. So, this will become T2, T1 23, T1 22 and it will be something like this. Okay. So, all this thing will be there and P1 tilde rho naught C1. I am so sorry. Okay, at x is equal to L, this is the vector here. Once we have this sort of an arrangement of the transfer matrix, and let us call this entire guy as the T matrix. Okay. So, there was a reason why I called this as T1, this is simply the T matrix. So, we can write this entire thing as T times this thing. Now, going back to our ECTR configuration, extended concentric tube resonator or just CTR with, so it is also named as ECTR. ECTR means extended concentric tube resonator. So, that means with neck extensions at the inlet and outlet. So, once we have got this kind of a thing, it will be a good idea to have a look at the boundary condition. So, let me go back to this figure. At this particular boundary, you have a rigid plate. You can also have a yielding plate, but for simplicity, because nothing is rigid really, we just assume the normal velocity to be 0, so that our analysis becomes a bit simple, but in principle you can have a coupled or one way coupled system, meaning that the you can have sort of a non yielding walls. So, here one needs to go to structural acoustics concepts. Here at this interface, the normal velocity or the basically the normal velocity of the fluid is equal to the normal velocity, the time rate of displacement normal to the plane of the plate, and your plate itself is governed by maybe your Kirchhoff equations. It could be a thin or thick circular plate with a concentric hole at the middle, and then your other condition is a pressure condition which acts like a loading condition, and this will radiate noise outside in the far field, and similarly here. But maybe we can those are still advanced topics and we probably would not be bothered about that, but my purpose of introducing this was that in real life imposing this rigid condition is only an approximation, because plates can sort of vibrate, they will yield no matter how thick you make them. So, but for our purpose we will introduce a rigid ball boundary condition there. As a result, what will happen, actually let me go back to this place, at this particular place A and this is B, Pa by rho naught C naught U A, that will become your minus j times cot k naught L A, assuming that this is L A and this is L B. Okay. So, here the velocity is obviously looking into the cavity, but if we have to really change the sign. So, here we have to put a minus sign. So, this will become plus. Similarly, at this point, the point B, we have P B by rho naught C naught U B. Now, the velocity, direction of velocity is not a problem, we just have L B. Okay. So, now with these conditions, we are good to proceed ahead, and let us get back to our this equations. What we will do is that now putting those boundary conditions, I would say P 2 0 and minus U 2 0, I mean of course tilde is equal to minus j rho naught C naught cot k naught L A, and your P 2 at L U 2 tilde at L is equal to j times rho naught C naught cot k naught L B. Okay. So, we will have these boundary conditions. Now, after a lot of manipulations, remember we are dealing with the system with the boundary conditions mentioned here, these ones. So, we need to somehow incorporate these boundary conditions in this equation. We had already done that in probably lecture 3, I reckon, and then we kind of slightly digressed and moved on to different things, probably perforated impedance expressions and all that. But now, once we incorporate these boundary conditions and simplify those equations that we discussed in the last in lecture 3, I believe, of this week, what we will get is basically the following transfer matrix between the points. If I call this point as 1 and this as point 2, just in the pipe just outside the perforate. So, we would get U 1 0 as something like this. Okay. T A, T B, T C and T D. So, we will get something like this, okay, where T A is given by T 11, that is your T 11 is really your this particular element. So, I am just writing down the equations, and we need to introduce a few more variables which basically come from the previous lecture 3. Once we simplify these things, you will be able to get it. So, this is like this. T B is your A 2 B 1, T C is your T 3 1 plus A 1 B 2, and T D is your T 3 3 plus B 1 B 2. So, what are A 1, A 2, B 1, B 2? What are those? So, A 1 is nothing but your another variable x 1 times T 2 1, T 2 1 we know, and T 4 1, and divide by F 1. Okay. And your A 2 is nothing but T 1 2 plus x 2 times 1 4, and B 1 is your x 1 T 2 3 minus T 4 3 by F 1, and B 2 is your T 3 2 plus x 2 times 3 4, and your F 1 is nothing but T 4 2. Everything is in terms of your known parameters. So, T 4 4 minus x 1 T 2 2 minus x 1 x 2 times T 2 4. So, what is, so we know now A 1 A 2 B F 1 is known, everything is known, only thing that is not known is your x 1, which is minus j times and k naught L A something like this. Okay. So, this is basically your inverse of once you kind of I mean this tan terms comes from these boundary conditions. Once you invert these things, and you will get to know that. So, once you know the 4 pole parameters, the transmission loss can be easily evaluated in terms of these expressions. So, I guess now is the time to jump on to MATLAB, and we have already written the code for that. So, here are some of the codes. Let me go through this only in a very succinct manner, the code. So, frequency range, the first and lower and upper bounds of 5 hertz and 2000 hertz. You can choose whatever values you want, but make sure that you are well within the plane wave region. This is more than plane wave region, just for the continuity sake. But so, the results will not be accurate up to this range, much before that, but just for argument's sake I have taken 2000 hertz. And porosity you can change, you can put it like 30%, and TH, DH. So, this is the thickness of the perforate holes, and now these are the parameters. So, you have 100 mm of annular area, 50 mm on each side. So, that will make up your entire 150 mm. Length is 400 mm. These are some of the values. So, I would choose, let us say let's begin with 200, that is your 0.5 times this thing, and this is your 1/4. So, let us keep like this. Now, perforated length is the difference of the extension length and this one. And actually what I would do is that really put this as 0 initially, and similarly this also is 0. So, we really have a CTR with no extensions, and this function calls in the transmission loss file, that is basically nothing but thing to compute the value. So, this is nothing new in this code, this always has to be used, but main thing is your transfer matrix. So, this is the key thing. So, it takes in the inner diameter, outer diameter, length, LA, LB, frequency value, that is your wave number at that frequency, thickness and diameter holes, porosity, and the grazing flow value. So, computes the pipe area, and now there are different perforated impedance expressions, that is why I reviewed it initially. So, this was for the stationary medium, and it is given in Selamet's paper in the book by Munjal, and also Melling has suggested the use of 0.85, but it would not make too much of a difference, and he suggested use of 0.06 rather than 0.006. So, it would not make too much of a difference for a stationary medium. This is only, this expression is only for a stationary medium. For a grazing flow medium, this is the one, but which is given in the Rao and Munjal's paper published a long time back, found out experimentally using an impedance tube test setup, and this is yet another expression for a perforate used rather more in the modern times, with the one given in the book or the paper by El Nadi and others. So, here we can have grazing flow and bias flow happening concurrently. So, we do not have a bias flow really. So, we just set the bias flow value to be 0 and put mg some value. So, these are all commented things, you do not have to worry about that. These are the A matrix written in a certain manner. So, I would not go through all the details, but these are basically of the form that pertains to your I guess the ones that we discussed here, isn't it? Something along these lines. Okay. So, A12 and A21 and all that. So, and this is your I matrix, that is identity matrix, and only when you have non-zero mean flow, non-zero grazing mean flow, you define these things, and C is equal to B/A when this is 0. When this is not 0, you can simply use C is equal to A, which I have commented out, and this is the guy what I was talking about, EXPM minus CL, and then you reshuffle or rearrange the matrices. This is the T1 matrix I was just talking about, this is the T matrix, and then these are your these are kind of your boundary conditions, which comes from the boundary condition. They are themselves are not the boundary conditions, but they arise these terms because of the implementation of boundary conditions due to neck extension. So, when LA and LB are both 0, x1 and x2 are tending to 0, they are 0, and as a result all these terms will go away, and this term will go away, this term will also go away, this term and this term, and the resulting expression will be much more simplified expression, and we will get a concentric tube resonator without extensions as the case that we are about to discuss. Then once we get TA, TB, TC, TD parameters, these are really 4 pole parameters, and now we convert this in terms of mass velocity by simple multiplication by characteristic impedance and division of this thing by this thing. So, this is fairly simple standard procedure. Main thing is these rather complicated expressions, which kind of can be nightmarish if you were to do it by hand calculation. So, I avoided doing that and used a little bit of computer algebra and some known literature to verify things. So, this I would suggest that you please practice it in your free time and using the longhand manner. Now, one more thing before we go into parametric studies, because from now onward we spend a few minutes to do some parametric studies. So, this is the perforate impedance file which I have written sort of separately. So, this is your rather complicated thing that I had shown you about. So, one needs to have little bit of practice with programming, so that will be useful. This can be done in Fortran, or there are so many things, Octave or Python or something like that, whatever you are comfortable with. And so, basically this file basically takes in all the parameters, and at the end it gives you the zeta parameter, that is your perforate impedance. So, porosity, mu, kinematic viscosity, and all these things are sort of well computed. Now, once we have these things, all we need to do is basically invoke this function. CH really means what color you would want to plot with. So, let us see what happens, and we can keep changing the value. So, I have set mean flow to 0.1, but we can put it to 0. So, let us do some transmission loss parametric studies. So, what we do, we just click this function, and with the parameter set, what we will do is that let us plot with black color. It should basically get us the transmission loss. You see, the maximum transmission loss is about, it follows the dome and trough pattern, exactly what you have for a simple expansion chamber. But do not be befooled by, do not just go with the fact that, well, this is looking just like a simple expansion chamber, so what is the use, why to do this algebra. I have already told you the reasons why we must use a perforated thing and do some extra work in deriving the equations and getting the proper perforated impedance expressions and all that. Although with this thing we would just get this thing, we will soon see how the extensions can dramatically affect the performance, can enhance the performance exactly like we saw for the extensions without any perforate. So, however, I must point out that the transmission loss performance of a ECTR, that is extended concentric tube resonator, will be quite different in terms of tuning of the length compared to a simple expansion chamber with neck extensions, for the simple reason that perforate impedance has a major role to play. And you notice the slide, the transmission loss is not identically 0, although it tends to that, practically it is 0, but there are troughs that are lifted. Now, expansion, this maximum transmission loss, some of the assignments that you would have solved, you can easily figure out that the maximum transmission loss was something like 20 times log m, something like that. So, this for the m is your area ratio. Okay. So, this would become 3 square, that is 9. So, this will become 4.5, and if we ask MATLAB to help us with the computation, we will get log 10 4.5. So, 13.06 for a simple expansion chamber. And what are we getting here? We are getting 13.27, very close to that, because of the perforate impedance, it has certain value. So, basically this troughs, these domes will keep on, has an increasing sort of a trend, and what we will do is that we will hold on to this figure, we will hold on and have some fun with it. Let's do some parametric studies. Let us put some mean flow 0.05, okay, and we hold on and plot with other color, which is red. So, in a fraction of a second it did give us, well, 1.35 seconds to evaluate for the whole frequency. Plane wave is very fast. So, it definitely does increase this thing, and the troughs also tend to increase the flow. And let's do one sort of 0.1 we can say. Remember, maximum Mach number that we can have is about 0.15 or something like that. So, this can be your blue color. So, this tends to increase and you have certain wiggles here, they start to show up. Let us do one more thing for 0.15, okay, and then let me use some other color, magneta, and we will see these peaks happening due to the mean flow at very low frequencies. Alright, these are all characteristic of the mean flow thing. So, what I would suggest is that let me close this figure and let us get back to our basic figure for the case when we have a zero flow, that is a stationary medium. Remember, the code will work because mean flow is already there. So, you just it is a matter of setting things. Now, once we do that, let us simply generate this figure, which we will have generated now, and hold on to it. And now play around with neck extensions. Now, let us do it in a step by step manner. So, what is half of 400? 200. So, 0.5 L other. So, extensions at the inlet, but there are no extensions at the outlet. Let us see what we get. So, we will get this kind of a curve, that is a phenomenal increase. We will do grid minor to have a greater insight. Before we start putting in extension at the outlet, there are quite a few things I want to discuss. You see, let us first put the data tip. Okay. So, forget about the peak can be anything, peak theoretically it is going to infinity. So, I do not really care about the amount of attenuation that is produced. The frequency at which it is happening is important. We are doing the discrete frequency at 11 hertz. So, 402. Now, the resonance of this chamber is 343 divided by basically C naught divided by 2L, C naught by L, C 3 by 2 into C naught by L. Basically, when you equate K naught L is equal to n pi, you get the axial resonances. So, L is the complete length of the chamber including the extension. So, the first trough is observed as the first resonance frequency of the whole chamber, that is at F is equal to C naught by 2L. So, 343 divided by 800 if you do, because L is your this thing, or C 343 divided by 0.8 if you do, you will get about 428 or something like that. Okay. You will get 428 if I were to click this, something like this, 428. Now, we remember for us extension concentric chamber with with extensions with extensions at the inlet and outlet, if we just had tube with L by 2 length, theoretically it would have exactly tuned the performance. We saw that. Okay. But then the thing is, does not really happen because of end correction effects. There were some end corrections. You would also have done some assignments related to that in the last couple of weeks or so. But here we are deliberately choosing at L by 2 and assuming only plane waves, still theoretically able to tune the performance. Okay. And that is really because of the perforated impedance. So, that is one point I want to tell, that just by looking at the configuration shown here, you would see that this is very much similar to your extension. So, basically if I were to use, let me use the space here. So, theoretically it is looking all very much sort of similar to this one. So, this is sort of equivalent to your this configuration, but because you have perforate, it plays a major role and you have very different looking, conceptually they are the same, but then you have quite different results. Okay. So, we have this sort of a thing. Okay. Now, we have the peaks here. So, what do we do with this? We have this thing here. So, basically by L by 2 we cannot really just tune it, we have to do some kind of a tuning, we have to tune the length, and anyways these are all based on plane wave models. So, this will obviously fail, there will be some higher order modes generated at the interface between the inlet pipe at the extensions and the annular cavity. There will be higher order modes generated due to the inductive effects of the evanescent modes. The effective length or the acoustic length of the pipes will increase. So, in order to tune that, we have to consider the geometrically smaller length. So, let me explain, but before we do that, let us also set this as 120 100, that is your 1/4, and at least draw the curve, obtain the curve. This is blue color. We see we have just readjusted the scales, and what we see now is that your these peaks, this peak definitely again happens at where it used to happen just when you have L by 2 and LB is 0, but now when we have extensions at both inlet and outlet 0.5 L and 0.25 L, the performance kind of enhances in the at higher frequencies, I mean beyond this thing. Although we would still see a trough here, the trough is lifted significantly, but another interesting thing is that even by choosing L by 4 we are not able to cancel the second trough, what we were able to cancel for a simple expansion chamber with extension. So, these are definitely the doings of the perforate. Okay. So, let us have some fun with it. what I would do is that basically get rid of the red curve, okay, and keep this thing intact and vary this thing. So, remember, based on the plane wave model, we are having the peak at this value at at this particular value, okay. So, and this is happening slightly before the trough. That means perforate what perforate is doing is that it is trying to kind of its effect is to basically increase the acoustic length. So, the resonance will occur a bit before. So, if we were to add the geometric length, that is if we were to if we were to subtract or reduce the geometric length in such a manner that your net length, your net acoustic length will be such that it cancels the trough, then we can sort of uplift the thing. Let us reduce it by a small amount, 10, let us say 10. So, let us do it with a red colored plot, and we will get this kind of a thing. So, it is there, it is approaching, and then if we were to let me use another color, perhaps red only, but sort of get rid of this thing and put 15 here, okay. And so, it is almost nullified the trough, okay. And if I were to maybe takes a little bit more, say 16 if I do. So, it is almost cancelled. So, basically what it means is that it is possible to account for the to tune the length, tune the extension length in such a manner that really your first peak, attenuation peak due to the resonator formed at the inlet cancels the trough, and you see a dramatic increase. This, if you compare, this was only 13, now this is much more 18, 5 dB attenuation, and this was trough, you are getting more than 20-25 dB attenuation. So, this is a fantastic performance. Now, another thing that I want to point out is that whatever extensions you are seeing, corrections or tuning you are seeing at the inlet will also hold for the outlet. It does not, plane wave kind of does not distinguish. So, we can sort of demonstrate this thing well, slightly more, but it is much better. So, if we were to slightly modify it by taking 14. So, this was 16, just take a bit less, maybe we can try with 15 as well. It will not be too different, that is all I am saying. So, you are nearly there, but if you make it like 15, so this is all done by hit and trial or trial and error. So, if you have to do it 14 and do the calculations. So, you have nearly the attenuation here due to the resonator formed at the outlet has almost nullified the trough. So, basically what has happened is that because of the perforate impedance, the exact tuning, if you choose L by 2, L A is equal to L by 2, it does not really tune it based on the plane wave theory, it kind of mismatches the trough. So, by choosing an appropriate length, we can actually tune the performance, and this happens by trial and error. But then we have to wait and watch. So, what happens is that for experimental results, there will be full contribution by the 3-dimensional modes. Okay, there will be evanescent waves that are generated at the interface, port chamber interface, or at the interface of where the perforated pipe starts and where the extension ends. So, at the interface there will be higher order modes generated. So, all the tuning that we are just talking about, these are just based on the plane wave analysis, but one really has to do either a finite element analysis of such perforated mufflers based on things like advanced techniques. Maybe we can discuss it in a different course called numerical mode matching or analytical mode matching, where we find out the performance of such mufflers incorporating 3-dimensional effects, and then choosing the length in such a manner that the 1D peak matches with a 3-dimensional peak, and then we can do all those tuning business. So, basically what I am trying to say is that the acoustic performance of a ECTR will be different from a expansion chamber with extensions, and that is largely because of perforates. Now, we will keep these results aside, and what we will do is that, let me make a simple change in the code. Let me use figure 1 and put a value, put some significant value of the mean flow 0.1 say. Okay. So, it is hard to now start tuning the performance when you have flow, but we will try to do something. So, I will initially to begin with put 0 here and 0 here and see what happens. So, we get this, we already started getting these kind of things that we are seeing here. Let me maximize the screen and I will do hold on, and now with the same value I will just uncomment it. Okay. And see what happens. So, the performance definitely has increased. So, how about I do grid on? And do this kind of a business. So, we see the one effect of mean flow definitely is that it basically increases the trough, it increases the trough as we can see here, but it also brings down the peak. So, all the peaks, attenuation peaks that were happening, that were occurring in these things, they have come down, and the mismatch definitely is there, but what I am saying is that attenuation is even at the lowest point, it is not, it is fairly significant, 12 dB or 12.5 dB, but the peaks have come down. So, the mismatch is there. If we were to sort of keep doing this iterations a few more times, so this can be a little annoying for the people who do not really want to do this. Let us put this as 14 and kind of go back to our figure and plot it again. So, we would want this peak really to completely cancel out the trough for a non-zero value. So, what we can do is that we can have a still higher value and do this exercise. So, I will set the grazing flow value to 0.15 and the extension length could be 0 to get a baseline case and see what happens. We start getting these wiggles or these peaks. I will put this hold on, say put hold on, and I will sort of put this as 10 and 10 and see what happens. These are all hit and trial really. So, the peak is tending to this value, but what happens if we choose say another values. Let us say if we choose a 5 or some 5, let us say we choose 5, okay, and see what we are tending to get. So, we are getting this kind of a thing. So, basically mean flow tends to reduce or decrease the end correction kind of a thing. So, we are nearly there. So, basically the point I am trying to make is that the mean flow definitely reduces the attenuation peaks that are present, but it still kind of tends to produce, it tends to produce kind of increased attenuation at frequency range where normally trough would occur. So, basically what I was saying is that then this the mean flow will have only a small effect on the end correction, but then in presence of mean flow it is rather hard, a bit difficult to tune the performance, at least in the context of one dimensional analysis. But especially when you have a large porosity like the ones that we have considered almost 30% porosity, which is like acoustically transparent, as we can see from here, 30% porosity. So, For such a case, end correction will be very small. End correction really is kind of significant when you have a very low porosity, okay, like something like less than 15% or things like that. And other thing that we also must note that impedance, perforated impedance is a function of many variables, which include, you know, hole diameter, thickness, and your mean flow, of course. So they also have to be investigated, and porosity, of course. So, you know, if we do it systematically, if we were to do it, we can find out a generalized curve fit based on a number of basically expressions for end corrections as function of all these parameters. So that will require a lot of you know, trial and error to find out things. So what I would suggest is that we leave these things here, and what we will do in the next week, that is week 9, we are really getting into the business end of the things and seeing things what happens practically. For the first time in this week we have investigated, we just seen a glimpse of what mean flow can do in terms of very realistic configuration. This configuration has the lowest back pressure because flow just goes through a straight pipe, it has the least back pressure, minimal. Now what it could do is basically this sets the scene for analysis of more complicated mufflers, like for example cross flow chambers. You know, when you have the flow has to necessarily come out of the pipes, and your it has to go through the pipes and leave the chamber from the other pipe and do all the business. And then we have to, there are different approaches what we could do, and then we will probably look at 3-pass mufflers, a bit more complicated, and discuss things when you have multi path propagation, different path the waves can take, and how do we do a network analysis of such a configuration. So this probably will be the subject matter of week 9, and possibly, you know, spilling over to week 10, and then we will see how we go with it. So till that time, thanks a lot.